You look up, dark sky, stars scattered like dust, and somewhere between them, something moves that shouldn't be there. July 1st, 2025, Atlas telescope in Rio Hurtado, Chile, picks up a dot. Routine scan. Larry Deneau from University of Hawaii reviews the data that night. Garden variety, near-Earth object, he thinks. Next morning, Hao TMs on a helicopter to Mauna Loa with his colleague John Tonry. Volcano damaged the road back in 2022. While they Hastu TM servicing equipment on that mountain, the alerts start flooding in. Follow-up observations from observatories around the world. 24 hours later, confirmed, this thing is ni TM Altetis from our solar system. 3 I's an Atlas, third interstellar visitor we know about. First was 1 I Oumuamua, 2017. Second was 2 I Borisov, 2019. Now this, and what it reveals changes everything we thought we understood about what our TMs out there. The trajectory tells the story. Hyperbolic orbit means it more TMs not bound by the sun. TM's gravity. Moving at 130,000 miles per hour when discovered. That ties are TMs 210,000 kilometers per hour. ESA calls it the highest velocity ever recorded for a solar system visitor. Objects do not TM move that fast unless they TM have been drifting a very, very long time. Michelle Bannister at University of Canterbury in New Zealand runs the models with her team. They publish on Archive July 11th for 2025, paper number 2, 507.05318. Their conclusion? 3I Atlas likely comes from the thick disk of the galaxy, the diffuse outer layer of primarily old stars surrounding our neighborhood. The speed, the trajectory, the numbers all point to one thing. This object has been traveling for more than 7 billion years. 7 billion years. Bannister puts it plainly. If true, 3I Atlas would be the oldest macroscopic thing we TM ever seen enter the solar system. If you value documented astronomical research and deep space discoveries like this, subscribe to our TMs, the best way to support our work. Also comment from which city you were hearing this from. This script is researched and factual, using sources including NASA, TM's official science reports, published July 3rd and updated through October 2nd, 2025, the European Space Agency TM's Yaku documents. Peer-reviewed archive preprint papers from August 25th, 2025, analyzing VLT spectroscopy data by Thomas Puzia and 26 co-authors, and Smithsonian Magazine's technical breakdown published August 28th, 2025, which synthesized findings from multiple observatory teams. Now back to the information. When Atlas spots it, the objective Puaus TMs at 4.5 astronomical units from the Sun, that data TMs 410 million miles, 670 million kilometers. Within Jupiter, bar TM's orbit. Temporary designation, A11PL3Z. Minor Planet Center lists it on their near-Earth object confirmation page, initially because the highly eccentric path might come close to Earth. Amateur and professional astronomers worldwide swing their instruments toward it. Within days, the truth emerges. Not threatening Earth, not even close. Closest approach to our planet will be 1.8 astronomical units, 170 million miles, 270 million kilometers, over 1.5 times the distance between Earth and Sun. And by the time that happens, 3 I Atlas will be on the opposite side of the Sun from us, hidden. But what catches attention is now TM, to just the trajectory. Itaubo TMs, what the thing is doing. Active comet behavior, coma forming. That TMs, the bright cloud of gas and dust that surrounds a comet nucleus when it heats up and sublimates, material breaking off. NASA Hubble Space Telescope images it on July 21st, 2025. Comet is 277 million miles from Earth at that moment. Hubble reveals a teardrop-shaped cocoon of dust streaming from the solid icy nucleus. Hubble are TMs tracking the comet along its hyperbolic path, so background stars streak in the exposure. By August 20th, Hubble observations give an upper limit on nucleus diameter. No larger than 3.5 miles, 5.6 kilometers. Could be as small as 1,444 feet, 440 meters across. 3I Atlas is far from the Sun and already shedding material. This shouldn't happen yet. James Webb Space Telescope observes August 6 with its near-infrared spectrograph. Martin Cordner, astronomer at Catholic University of America, leads the investigation. Team submits preprint paper to RCIV August 23rd. Paper number 2508.18209. What Webb finds in the coma stops everyone cold. Carbon dioxide, massive amounts. The CO2 to water ratio is among the highest ever seen in any comet. Not just high. Exceptional. Stephanie Milam, astrochemist at NASA Goddard Space Flight Center, works on the observations. She suggests 3. I-Atlas may have developed what she calls a cooked shell on its surface during billions of years floating through near absolute zero void, constantly bombarded by cosmic rays. CO2 ice is created in that shell. Now the sun heats it, vents into the coma. Webb also detects water vapor, carbon monoxide, carbonyl sulfide, water ice, all breaking off as the comet heats up, but the carbon dioxide dominates. If this composition reveals where 3 I-Atlas formed in its original protoplanetary disk, Milam says it likely formed pretty far out, where the carbon dioxide ice line is, the boundary beyond which CO2 freezes solid in the disk of gas and dust around young stars. These are the first chemical clues, but they, temporarily not the strangest, very large telescope in Chile, X-shooter and UV-ES spectrographs. Observations run from late July through August 21st, 2025. Heliocentric distances from 4.4 astronomical units down to 2.85. Thomas Puzia at Pontifical Catholic University of Chile leads the spectroscopy team. 26 co-authors. Paper submitted to Archive August 25th. Number 2, 508.18382. What they detect in 3 I-Atlas should exist. Nickel. Gas phase, nickel atoms. Production rate measured on August 21st at 2.85 astronomical units, 4.6 grams per second. 0.16 ounces per second. Iron, none detected. This breaks the rules. Nickel and iron always appear together when sublimated from comets. Always. You see one, you see the other. They alchemically chemically bound in the same mineral phases, same dust grains, same parent material. Finding nickel without iron is like finding smoke without fire. Shouldna Borstiam MT happen. The VLT team detects nickel at all observation times. Iron only appears at heliocentric distances smaller than 2.64 astronomical units. By that point, 3 I-Atlas is closer to the sun and heating rapidly. The nickel to iron ratio, extreme. Making 3 I-Atlas exceptional compared to every solar system comet, and even compared to 2 I-Borisov. Cyanide also appears. CN emission detected. Production rate on August 21st, 17.6 grams per second. 0.62 ounces per second. But the behavior is bizarre. The heliocentric distance scaling is steep. Nickel production rate follows R to the negative 8.43 power. Uncertainty plus or minus 0.79. Cyanide follows R to the negative 9.38 power. Uncertainty plus or minus 1.2. Those exponents mean production rates explode as 3 I-Atlas approaches the sun. Not linear growth, exponential. The VLT team runs energetic calculations, activation barriers, sublimation energies. Their conclusion: this behavior is inconsistent with direct sublimation of canonical metal phases or sulfide phases, something TMs, releasing the nickel through a low activation energy process. Options: photon-stimulated desorption from dust, mild thermolysis of metallated organics, nickel-rich nanophases, possibly nickel-carbonyl-like complexes. Puzia says it plainly. We just cracked open the door to a whole new world of chemistry that we never had access to before. If nickel tetracarbonyl exists in the dust grains, that explains part of it. Highly volatile molecule. Breaks apart easily under UV light, releases nickel and carbon monoxide. Could account for high activity levels while still far from the sun. But nobody has ever detected nickel tetracarbonyl in a comet before. This would be first. Daryl Seligman at Michigan State University works on initial characterization. Team publishes on ARCIV July 9th, paper number 2, 507.02757. They catch it right before peak activity. Observations follow basically every night for weeks. The velocity alone is remarkable, 130,000 miles per hour, much faster than Oumuamua or Borisov, consistent nudging from gravity of large-scale structures. Giant molecular clouds, spiral arm passages, 7 billion years of drift adds up. If 3 I-Atlas truly passed through the galactic disk multiple times over billions of years, Kortner points out what that means: passed through interstellar clouds. Star-forming regions where massive stars are born, supernovae going off, a whole range of environments. Radiation? shock waves, chemistry happening on the surface, layer by layer. October 3rd, 2025. 3. I-Atlas makes closest approach to Mars, 30 million kilometers, about 18.6 million miles. ESA, Mars, Express, and ExoMars. Trace Gas Orbiter swing instruments toward it. HRSC camera, Cassis camera, both designed to photograph the Martian surface from hundreds to thousands of kilometers away. Now, pointing at a comet 30 million kilometers distant, the comet itself covers less than a pixel, but the halo of gas, the tail streaming behind, those show up. Omega and Spikum spectrometers on Mars Express try for spectral measurements. Nomad spectrometer on TGO does the same. Success depends on brightness, on how much water the comet contains, how much escapes its tail, Mars observes. Records, data streams back. October 29th, 2025. Solar conjunction begins. 3. I-Atlas dips into the glare of the sun. Earth-based observatories lose sight of it. Fox Weather reports on October 1st that the comet will disappear from Earth. DOTM's view this week, leaving detective work to spacecraft far from our planet. October 30th, 2025, Perihelion, closest approach to Sun, 1.4 astronomical units, 130 million miles, 210 million kilometers, just inside Mars orbit. NASA reports perihelion around October 30th. ESA says late October. Wikipedia specifies October 29th. Close enough that the difference is measurement, uncertainty, and orbital calculation. Precision. During solar conjunction, observatories can now TM, see 3i Atlas from Earth. Too close to solar disk, blinding glare. But spacecraft positioned elsewhere in the solar system have different lines of sight. Parker Solar Probe, launched 2018, primary mission, study the sun, touch the solar corona. The probe carries WISPR, wide field imager for solar probe. Back in July 2020, WISPR imaged comet Neowise shortly after close approach to Sun. Study authors publishing in BBC Sky at Night magazine on October 1st, 2025, say Parker should be able to observe 3i Atlas with WISPR from late September through early November. Perfect timing. The probe is positioned to watch the comet during perihelion passage. When Earth-based telescopes see nothing, Parker sees everything. September 25th, 2025, IFL Science reports something unexpected. NASA forecast model predicts a coronal mass ejection will collide with 3i Atlas. Maybe already hit it by September 24th. CME, massive burst of plasma and magnetic field erupting from the sun, traveling millions of miles per hour. Slamming into the comet during perihelion approach. Spaceweather.com reports the forecast. A CME collision with an interstellar object. Not often that happens. Only third interstellar visitor we know about. First time we might observe a CME impact on one? What happens when a coronal mass ejection hits a comet? Compression of the coma, magnetic field interaction, possible tail disruption, increased sublimation from shock heating. The chemistry could change. Volatile release could spike. If Parker Solar Probe captures this with WISPR, the data will be unprecedented. 3i Atlas survives perihelion. It has to. The trajectory is already calculated. Exit path locked in, but what state will it be in? John Noonan, astronomer at Auburn University, watches closely. He references what happened to 2i Borisov. Before perihelion, Borisov showed mixture of carbon monoxide and water vapor. After perihelion, water source seemed to largely run out. NASA Swift mission data confirmed it. Will 3i Atlas undergo similar transformation? Will the surface-cooked CO2 shell burn off? Revealing deeper nucleus material unchanged since formation 7 billion years ago. Material preserved from the ancient protoplanetary disk of a star system so distant we may never identify which one. Early December 2025, 3i Atlas emerges from behind the sun. Reappears in Earth or TMN's night sky. Ground-based telescopes swing back toward it. First priority, detect changes. Compare spectra from before perihelion to after. Has the CO2 to water ratio shifted? Is iron now detectable alongside nickel? Or does nickel still dominate? Did the cyanide production rate change? Are new volatile species outgassing that Werner TM visible before? Methanol, formaldehyde, methane, ethane, hydrogen cyanide, ammonia. Cordner lists them. The objective is to get detailed chemical inventory inside this object. Revelatory for comparisons with our own solar system. December observations also target the nucleus directly. Hubble could detect it. Too faint. Too much coma in the way. Upper limit of 3.5 miles diameter, lower limit of 1,444 feet, but actual size unknown. JWST attempts in December to use additional instruments, peer through the hazy coma, measure the nucleus within. That radius measurement is critical. It tells us exactly how rapidly material is breaking off, sublimation rate per unit surface area, composition density, whether 3I Atlas is a loose rubble pile or solid ice chunk. March 2026. 3I Atlas approaches Jupiter. Avi Loeb, astronomer at Harvard, publishes on Medium, July 29th, 2025, discussing possibility of intercept using Juno spacecraft. Juno launched 2011, arrived at Jupiter 2016, primary mission studying Jovian atmosphere, magnetosphere, and interior structure, but Juno is still functional, still maneuverable. The trajectory of 3I Atlas brings it near Jupiter on its outbound journey, not close flyby. But within observation range, could Juno pivot? Observe an interstellar comet with instruments designed for gas giant? Spectrographs could measure coma composition. Cameras could image nucleus if close enough. Particle sensors could detect dust grains shed from 3I Atlas. Even if Juno only captures distant data, Tau-TM's another vantage point. Another piece of the puzzle, ESA JUICE mission might have the best view. Jupiter Icy Moons Explorer launched April 2023, currently en route to Jupiter via gravity assist flybys. As of October 2025, JUICE is close to the Sun, using its main high-gain antenna as heat shield, communicating via smaller medium-gain antenna at much lower data rate, far from Earth. On the other side of the Sun, SA FAQ documents explain JUICE will attempt observations of 3I Atlas in November 2025 using multiple instruments, cameras, spectrometers, particle sensor, coordination with NASA Europa, Clipper mission being considered. Both spacecraft carry ultraviolet spectrographs, twin observations, stereoscopic data. Because JUICE is far from Earth and behind the Sun during November, data 1T arrive until February 2026. 2 months delay. But when those observations download, they might capture 3I Atlas in a very active state, post-Perihelion, shedding material rapidly, nucleus potentially fragmenting, chemistry in flux. David Jewett at UCLA leads Hubble observations. Published on ARC of August 6th, paper number 2508.02934. He speculates about interstellar object population. We know solar system started with a protoplanetary disk. A lot of material in that disk was lost, kicked out. 90 or 99% ejected to interstellar medium. Maybe the galactic disk is full of comets ejected that way. If that TAS, Choros TM's the case, Jewett says, there should be a hell of a lot of them. 3 interstellar objects detected so far. Oumuamua, Borisov, 3I Atlas. Oumuamua was unique, detected only on its way out. No visible activity. Rapidly shifting brightness suggested highly elongated object tumbling end over end. Also unexpectedly accelerated due to some force other than gravity. Puzzled astronomers. They didn't detect outgassing to explain it. Many scientists believe gases escaping from Oumuamua were too faint to detect. Jewett speculates Oumuamua might be evolved form of object like Borisov or 3I Atlas. Lost most volatile gases from previous close pass by some other star. Burned out husk. But until more interstellar objects are found, we can only wonder. Vera C. Rubin Observatory in Chile. Expected online soon. State-of-the-art survey telescope. Projections say it will discover dozens more interstellar visitors in coming years. Atlas, network expanding, more eyes on the sky, better detection algorithms, faster follow-up observations. Kortner says it plainly. This is only the beginning. But back to 3I Atlas and what we free learning right now. The chemical fingerprint is unprecedented. Nickel without iron. CO2 dominating water. Steep production rate curves. None of this matches solar system comets. All of it points to formation in a different stellar environment. Different chemistry. Different temperature gradients in that ancient disk. Different radiation exposure. Different everything. The debrief publishes analysis. September 27th, 2025. Unusual discovery suggests 3I Atlas is anomalously massive. Astrometric data from recent observations, lower limits on mass and size. Loeb derives new paper. The numbers don't attempt to constrain composition, he notes, but they constrain total mass. If 3I Atlas is denser than expected. If the nucleus is larger than Hubble upper limit suggests, then the total volatile inventory is enormous. Billions of tons of ice, Organics? Metals? All forged in another star system, all traveling 7 billion years to arrive here, now, October 2025. Why does it matter? Because every interstellar object is a sample return mission we didn't TMT have to launch. The universe delivers these samples to our doorstep, for free. We just have to watch, measure, record. 3. Atlas left its birth system so long ago that the star might not even exist anymore. Parent star could have gone supernova, could have left main sequence, expanded into red giant, shed outer layers, collapsed into white dwarf. The planetary system where 3 Atlas formed might be debris field now, might be nothing, but the comet remembers, frozen time capsule. Chemistry locked in ice for eons, until the sun heats it, until the volatiles sublimate, until spectroscopy reveals secrets. The nickel emission particularly fascinates researchers. Metallated organics breaking down, nickel-rich nanofaces, these RENA T&M to materials we see in our comets. These suggest formation conditions where nickel concentrated differently. Maybe the protoplanetary disk had localized pockets of metal-rich dust. Maybe supernovae ejecta seeded the disk with specific isotopes and elements. Maybe the chemistry of that distant star system was fundamentally different from ours. VLT data introduces measurable, repeatable, unprecedented chemical fingerprint. Nickel without iron. Benchmark observation now. Above the norm. News publishes August 29th, 2025. Cannot be dismissed as noise. Cannot be explained by conventional cometary physics. This is the statement researchers are making. Not speculation. Conclusion from data. The production rates tell their own story. Log Q of CN equals 23.61 on August 21st. Uncertainty plus or minus 0.05. Log Q of nickel equals 22.67. Uncertainty plus or minus 0.07. Those are molecules per second and atoms per second respectively. Converting from log scale, 4 trillion cyanide molecules every second, 470 billion nickel atoms every second. From an object maybe a few miles across, maybe smaller. That sublimation rate is extraordinary for a heliocentric distance of 2.85 astronomical units. Most solar system comets are barely active at that distance. 3 Atlas is gushing. The coma spectrum shows dust-dominated composition, red optical continuum slope, 21 to 22% per thousand angstroms, fairly constant across observations, but buried in that continuum are emission lines, CN bands, nickel lines, multiple nickel transitions detected, phi lines mostly absent until closer to sun. The spectroscopic signatures are clean, high signal to noise, no ambiguity. When iron finally appears below 2.64 AU, the ratio is still wrong. Nickel vastly exceeds iron. In solar system comets, you get roughly equal amounts or iron dominant. Here, nickel wins by orders of magnitude. The VLT team searches for other metal lines. Sodium, nothing conclusive. Magnesium, nothing. Calcium, nothing, just nickel. And late arriving iron. What about water? The 3 sigma upper limit on OH at 3.17 AU is 7.76 times 10 to the 23rd molecules per second. Fat hour TM's upper limit. Actual value likely lower. OA forbidden line, not detected. C2? No. C3? No. NH2? No. All the common cometary emissions that should dominate at 3 AU, missing or faint. Instead, we get nickel and cyanide blazing bright. Coma structure from Hubble imaging shows teardrop shape, dust cocoon, tail forming. By August observations, tail is visible, streaming away from nucleus. Direction exactly opposite sun. Radiation pressure and solar wind pushing material outward. Standard comet behavior, but the composition of that tail is anything but standard. Spherex observes August 7th through 15th. Spectrophotometer for the history of the universe. Epoch of Rionization and ICE's Explorer. NASA mission designed to survey entire sky in infrared. Creates spectroscopic maps. 3. Atlas appears during observation window. Spherex team captures spectral data. Research note published shortly after. The infrared signature complements visible light observations. Different wavelengths probe different molecular species, different temperature regimes, different grain sizes in the dust. Next Big Future publishes September 5th, 2025. James Webb and Spherex reveal dust around 3I. Atlas is 95% carbon dioxide, only 5% water, almost no carbon monoxide, completely unlike any comet ever observed. The piece quotes the spectroscopic findings. The ratio is extreme. If the coma reflects nucleus composition, this thing is built different. But maybe the coma does not TM reflect bulk nucleus composition. Maybe what we, TM, are seeing is surface layer. The cooked shell hypothesis. Billions of years of cosmic ray bombardment. Radiation processing. Original ices locked deeper. Surface transformed. When perihelion heating penetrates past that shell, composition might shift. Water might dominate. CO2 might drop. The December observations will test this. If you value documented astronomy history and extreme cosmic chemistry like this, subscribe Arwinaz IT or TM as the best way to support our work. Also, comment from which city you are TM, where I'm hearing this from. This script is researched and factual, continuing to draw from NASA, TM's Planetary Defense blog entries updated through October 2nd. Archive preprint number 2, 508.18382, Analyzing Dramatic Nickel Emission, published August 25th by Rohan Rahatgaonkar and the full VLT team, and real-time observations documented across multiple space agency databases. Now back to the information. The trajectory after perihelion is already calculated. 3I Atlas swings around Sun, accelerates on outbound leg, gravity assist from solar encounter adds velocity, current speed of 130,000 miles per hour will increase. By the time it passes Jupiter in March 2026, it might hit 150,000 miles per hour or more, then keeps accelerating as it climbs out of solar gravity well, eventually reaches terminal velocity relative to local standard of rest in galaxy, drifts. Decades turn to centuries, centuries to millennia, millennia to millions of years. Maybe in 10 million years it encounters another star system. Maybe not. Statistically, interstellar space is vast, empty. The distance between stars averages 4.2 light years. The T-Warsho TM's 25 trillion miles, 40 trillion kilometers. 3I Atlas, moving at terminal velocity of maybe 200,000 miles per hour, covers 1 light year in 3,000 years. 4 light years, 12,000 years. And the TAS road or TMS, if it were TMs heading straight toward the next star, which it is, not by TMT. Trajectories are random. Gravitational deflections from passing molecular clouds, spiral arm density waves, galactic tide. Every perturbation alters the path slightly. Over 7 billion years of drift test out. 3I Atlas could have passed hundreds of stars, thousands, or none. Could have spent entire journey in deep void. The chemistry suggests some stellar encounters, some radiation exposure beyond cosmic ray background. But we can now trace the path backward. The galaxy rotates. Stars move. The differential rotation of galactic disk scrambles all trajectories older than a few 100 million years. Trying to identify source system is futile. Now what we can do is measure what 3I Atlas is now, what it releases, how it behaves. The November and December observations are critical. Post-perihelion data. Changed composition, possibly changed structure. Comets can fracture. Perihelion stress, thermal shock, rapid heating on sunward side, frozen night side. Differential expansion, cracks propagate, nucleus splits. If 3I Atlas is rubble pile held together by ice, perihelion might break it apart. We could see multiple fragments in December. Each fragment would have its own coma, own tail. Spectroscopy of fragments might show compositional heterogeneity, different pieces with different chemistry. That would reveal layering in original nucleus. Core versus mantle material. Formation history written in ice or 3. I-Atlas might survive intact. Solid nucleus, strong structure. In that case, December observations should show continuous coma, single tail, consistent spectral signature, slight shifts in composition ratios as deeper material sublimits, but overall coherent object. The size measurement is crucial either way. If Hubble couldn't that's TM, T-resolved nucleus, JWST might, near-infrared camera, high angular resolution, deep exposures, subtract coma contribution, isolate nucleus signature. Even if nucleus is at lower end of size range, 440 meters, JWST should detect it at December, our TM's distance. If nucleus is few kilometers across, definitely visible. That radius combined with sublimation rate gives mass loss rate. Total volatile inventory, a lifetime. How much longer will 3I Atlas keep outgassing? Depends on total mass. If nucleus is small, a few hundred meters, and current sublimation rate continues, it could lose significant fraction of mass during solar system passage. Might exit smaller than it entered, might even fragment completely, become debris stream. If nucleus is large, a few kilometers, then current mass loss is negligible, barely touching surface reserves. object could survive thousands more stellar encounters, billions more years of drift. Eventually, the volatiles are gone, becomes dormant, dead comet, looks like asteroid, no activity, just dark nucleus, hydrocarbons coating surface, radiation process tars. That might be what Oumuamua was, evolved interstellar comet. All volatiles lost from previous perihelion passages in other systems. The 3I Atlas case raises fundamental questions. How many interstellar objects pass through inner solar system annually? Estimates vary wildly. Before Oumuamua, estimates were 1 per century. After Oumuamua and Borisov detections, revised upward, maybe 1 per year, maybe several. Depends on local density of interstellar population, depends on galactic ejection rates, depends on average velocity, all uncertain. Rubin Observatory will answer this. Wide field, deep sensitivity, rapid cadence. Survey entire visible sky every few nights. Detect moving objects down to faint magnitudes. Fast-moving objects get flagged. Trajectories calculated in real time. Hyperbolic orbits identified immediately. Network alerts. Global community. Follow-up begins within hours. Projections say Rubin will detect dozens of interstellar objects per year once fully operational. Dozens. That changes everything. From rare curiosities to regular occurrence, from individual case studies to population statistics, we can measure size distribution, velocity distribution, compositional diversity, activity levels, all the parameters needed to understand where these things come from, how they form, what they tell us about planet formation in general, because every planetary system sheds comets, gravitational scattering during planet migration, close encounters, orbital instabilities. Most ejected material ends up in interstellar space. If our solar system ejected 90% of its original mass, other systems do the same. Multiply by 400 billion stars in galaxy. The interstellar comet population is massive. 3I Atlas is messenger from that population. Sample of distant chemistry, 7 billion year time capsule. The spectroscopy reveals what was frozen into it at formation. The outgassing reveals how interstellar environment modified it. The trajectory reveals how long ATM has been traveling. Every measurement adds detail to the story. The nickel emission remains the biggest puzzle. VLT team explores multiple hypotheses in their paper. Photon-stimulated desorption requires UV photons to liberate nickel from dust grains. Solar UV flux at 2.85 AU is sufficient. Grain composition matters. If grains are carbon-rich with embedded nickel nanoparticles, UV photolysis could release atoms efficiently. Requires specific grain structure, though, not typical of solar system dust. Thermolysis of metallated organics means nickel chemically bonded to organic molecules. Heat breaks the bonds. Nickel released. But what organics, and how did nickel get incorporated, requires formation conditions where gaseous nickel and organic vapors coexisted and reacted. Maybe in warm inner regions of protoplanetary disk before ices formed, material later transported outward, mixed into comet-forming zone, frozen in. This scenario demands complex dynamical history for the source system. Nickel carbonyl hypothesis is cleanest, nickel tetracarbonyl. Chemical formula, NiCO4, highly volatile. Sublimits at negative 170 degrees Celsius. Decomposes under UV producing nickel atoms and carbon monoxide. Known industrial compound. Used in refining. Never detected in space before, but conditions for its formation exist. Requires metallic nickel dust, carbon monoxide gas, low temperatures, catalytic surface reactions, all plausible in cold outer regions of protoplanetary disk. If 3I Atlas contains nickel carbonyl ice, that explains early activity, explains nickel without iron, explains steep production rate curve. As comet heats, carbonyl sublimates first, releases nickel. Iron-bearing minerals require higher temperatures, stay frozen until closer to sun. By 2.64 AU, iron minerals start sublimating. Iron emission appears, but nickel already dominated for weeks. The CN emission adds another layer. Cyanide in comets usually comes from HCN, hydrogen cyanide. Photodissociation by solar, UV produces CN radicals. Those radicals emit visible light. Diagnostic lines in violet and blue spectrum. VLT detects multiple CN band systems. Strong signal. Production rate 17.6 grams per second equals roughly 4 trillion molecules per second of CN radicals. Implies even higher production rate of parent HCN because not all HCN photodissociates immediately. HCN is common in comets, indicator of organic chemistry. Carbon-nitrogen bonding requires nitrogen-rich formation environment. 3I Atlas showing strong CN suggests significant nitrogen inventory. Combined with CO2 and CO detections, The CNO inventory, carbon, nitrogen, oxygen, is substantial. These are the building blocks: prebiotic chemistry, amino acid precursors, sugar precursors. Not saying 3. iAtlas contains life, saying it contains the ingredients. Every comet contains some organics. But composition ratios differ. 3. iAtlas tilts heavily toward carbon dioxide. Solar system comets tilt toward water. That difference maps to formation temperature. CO2 condenses at slightly warmer temperatures than water ice in low-pressure protoplanetary disk environments. If 3 iAtlas formed in region where CO2 dominated condensation, it records colder outer disk conditions than typical solar system comets, or records different gas phase chemistry in the source disk, different C to O ratio in the gas, different carbon partitioning between CO, CO2, methane, organics. Isotope ratios would clarify this: deuterium to hydrogen ratio, carbon 13 to carbon 12, nitrogen 15 to nitrogen 14, oxygen 18 to oxygen 16. These ratios are fingerprints. They reveal formation temperature, reveal chemical processing history, reveal interstellar modification. But measuring isotopes in a comet coma is hard, requires high spectral resolution, long exposures, bright targets. 3 iAtlas is faint, fast-moving. The spectroscopy obtained so far lacks sufficient resolution for isotope measurements. Maybe JWST can do it, near-infrared spectroscopy of specific molecular bands, or maybe we wait for future missions. Next interstellar comet, better instruments, longer observation windows. The dust composition also matters. VLT sees dust continuum, red slope, but dust grain composition is unknown. Are grains silicate, carbon, mix? Grain size distribution affects scattering, affects color, affects how much light we see. Polarimetry measurements would constrain grain properties. Polarization of scattered sunlight depends on grain size and refractive index. Nobody has published polarimetry of 3 iAtlas yet. Maybe ongoing observations will. The Hubble imaging shows dust morphology, teardrop shape. Asymmetric. Sun-heated side releases more dust, radiation pressure pushes dust into tail, dust tail curves, follows orbital mechanics. Slower grains lag behind comet, faster grains pushed ahead, creates curved streak, classic comet appearance, except this one ITM's from another star system. The 3 interstellar objects detected so far show diversity. Oumuamua, inactive, elongated, accelerating mysteriously. Borisov, active, typical comet-like composition, normal behavior. 3 iAtlas, active, bizarre composition, extreme velocity. 3 data points. Not enough for statistics, but enough to show interstellar population ISNI TM TT not uniform. Different formation environments, different histories, different fates. Oumuamua pop TMs. Acceleration puzzled everyone. Non-gravitational force, no visible outgassing. Proposals ranged from hydrogen ice to solar sail to alien probe. Consensus now leans toward outgassing of hydrogen or other invisible species. But weird shape remains unexplained. Aspect ratio of 6:1 or 10:1 depending on models. How does something that elongated form? Collision fragment? Tidal disruption remnant? Agglomeration of smaller pieces? No good answer yet. Borisov looked normal. Water-rich, co-rich, dust production, familiar spectroscopic signatures, almost disappointing in its normalcy, like solar system comets. Suggested common formation processes across different protoplanetary disks, universal comet chemistry. But then 3 iAtlas arrives. Throws that idea out. Maybe Borisov represents majority. Maybe Oumuamua and 3 iAtlas are outliers. Or maybe diversity is the rule. Every star system produces different comet populations, different volatile ratios, different structures. We won't attempt know until we detect hundreds, build statistical sample, measure distributions. The challenge is detection. Interstellar objects are fast, appear suddenly, leave quickly. Atlas detected 3 iAtlas on inbound leg. Good timing. Gave months of observation window. But what about objects approaching from behind Sun or passing through solar system on trajectories that never enter inner regions? Those go undetected. We only see the ones that happen to cross our field of view, that happen to get close enough to be bright. Selection bias is enormous. Rubin Observatory partially solves this. Wider coverage, deeper limits. But even Rubin has blind spots. Daytime sky, southern hemisphere gaps. Very fast objects that move too far between exposures to be linked. Every survey has limits. Total interstellar flux through solar system is probably much higher than detection rate. Modeling by Bannister and colleagues suggests arrival rate of interstellar objects in inner solar system might be 1 to 10 per year for objects larger than 100 meters. We detect a tiny fraction of those, 3 in 8 years. That implies most pass through undetected. Lost opportunity. Every interstellar visitor carries unique information. Miss one, lose that data forever. 3, Atlas data accumulation continues. TESS observes transiting exoplanet, survey satellite, designed to monitor star brightness, detect exoplanet transits. But TESS field of view sweeps across sky. If 3, Atlas crosses TESS field, satellite records brightness variations, short cadence photometry, detects rotational period of nucleus if present, detects outburst events if they occur, detects fragmentation if it happens. Swift Observatory observes X-ray and UV telescopes. If 3, Atlas is bright enough in UV, Swift characterizes OH emission, water photodissociation product. Also looks for X-ray emission from solar wind interaction with coma. Comets occasionally produce X-rays when solar wind ions impact neutral coma gas. Charge exchange process excites ions, produces soft X-rays, diagnostic of coma density and solar wind conditions. Perseverance rover on Mars might image 3I Atlas during October, close approach to Mars. Rover carries cameras, MASCM-Z, wide-angle imagers. If comet is above Martian horizon during imaging window, Perseverance could capture it, low resolution, tiny dot, but Mars-based observation nonetheless. Parallax measurement combined with Earth-based observations would refine distance and trajectory. Small improvement, but every bit helps. Curiosity rover also on Mars. Older, fewer imaging capabilities, but still functional. If both rovers image simultaneously, stereoscopic observations from Martian surface, 30 kilometers apart, gives baseline for precise angular measurements. Europa Clipper launched October 14, 2024, currently en route to Jupiter via Mars Gravity Assist. Scheduled Mars flyby March 1st, 2026. Timing is wrong for 3 Atlas observation during that flyby. But Clipper carries ultraviolet spectrograph, Europa UVS. After Mars flyby, Clipper continues to Jupiter, arrives April 2030. 3 Atlas will be long gone by then. But Clipper juice coordination for November 2025 observation window might work. Both spacecraft have UV instruments, complementary wavelength coverage, joint observation campaign. Lucy mission launched October 16, 2021, heading to Trojan asteroids. Currently in solar orbit, Lucy carries high-resolution imager, LORI, IF-3 Atlas. Trajectory passes through Lucy, field of regard. Spacecraft could slew an image, long-distance observation. Probably not worth fuel expenditure for spacecraft targeting specific asteroids. But possibility exists. A Psyche mission launched October 13, 2023, heading to asteroid 16 Psyche, metal-rich body. Psyche spacecraft carries multispectral imager, magnetometer, gamma-ray spectrometer, none particularly useful for comet observations. But gamma-ray spectrometer might detect nuclear interactions if cosmic rays hit 3I Atlas coma. Extremely unlikely. Coma too diffuse, cross-section too small, but technically possible. The wish list for observations includes mass spectrometry, direct sampling of coma gas, measure molecular masses, isotope ratios, species identification. No mission is positioned to do this. Would require spacecraft close flyby, within hundreds of kilometers, passing through coma, instruments sampling directly. We did this with solar system comets, Giotto at Halley, Stardust at Wild 2, Deep Impact at Temple 1, Rosetta at 67. P. But those were targeted missions. Years of planning. Spacecraft designed specifically for comet rendezvous. 3 Atlas arrived with 3 months warning. No time to launch intercept mission. No existing spacecraft on intercept trajectory. We observe from distance, spectroscopy, imaging, indirect measurements. Better than nothing, but frustrating. This thing traveled 7 billion years. Arrives in our solar system, visible for a few months, then gone forever. We get one chance. Avi Loeb proposes future infrastructure. Network of fast response spacecraft on standby, parked at Earth-Sun L1 or L2 Lagrange points, ready to launch toward any detected interstellar object. High delta V propulsion, solar sails, ion drives, could reach comet within weeks, deploy impactor, deploy lander, deploy penetrator, sample collection, dust analysis, surface imaging, everything we wished we could do with 3I Atlas. Cost would be billions, But science return would be unique. Ground truth on interstellar material. No other way to get that data. Sample return missions to interstellar objects are ultimate prize. Bring back pristine material from another star system. Laboratory analysis, mass spectrometry, microscopy, crystallography, everything. Project Lyra is design study for interstellar object intercept mission. Published concepts for Oumuamua chase. Concluded mission was possible with existing technology, solar Oberth maneuver, dive close to sun, use solar gravity assist plus chemical propulsion, kick velocity up to escape speed, chase Oumuamua, catch up in 20 to 30 years, but launch window closed. Oumuamua too far now. For 3I Atlas, launch window is now, next few months. After that, comet accelerates away. Catching it becomes impossible even with Oberth maneuver. Nobody is launching, no mission is ready. So we watch it go, take all the remote observations we can, archive the data, learn what we can, wait for next one. Statistically, next interstellar object arrives within a year or two, maybe sooner if Rubin begins operations. Could be comet, could be asteroid, could be something weird like Oumuamua. Every detection teaches us, every spectrum adds detail. Population properties emerge from individual cases. 3I Atlas will exit solar system by 2027. Pass beyond Neptune and TM's orbit. Continue outward, Kuiper belt. Scattered disk, Oort cloud inner boundary at few thousand AU. 3I Atlas will be invisible long before then. Last observations, probably early 2026, after Jupiter flyby in March. Then too faint, too distant, lost against background stars, it will drift. Speed, relative to Sun, approximately 80 kilometers per second, after accounting for solar gravitational deceleration. Theta. TMA's 179,000 miles per hour. Exits solar gravitational dominance around 100,000 AU. Takes over 500 years at that speed. Then true interstellar space again, back to the void it came from. Over next billion years, might encounter another star. Might plunge into another planetary system, might be detected by someone else on TM's telescopes, might impact a planet, might fragment in stellar wind, might survive unchanged, no way to know. But for a brief window in late 2025, it was ours to study. Humanity pointed every available telescope at it: Hubble, Webb, VLT, Atlas, Spherex, Mars orbiters, future JUICE observations, dozens of papers published or in preparation. Hundreds of astronomers involved. Global collaboration, shared data, open access. The VLT paper alone lists 26 authors from 13 institutions across 6 countries. PUSIA leads. Co-authors contribute spectroscopy, photometry, orbital calculations, chemical modeling. Everyone brings expertise. Result is comprehensive analysis, not perfect, plenty of unknowns, but best we can do with available tools. The nickel finding stands as primary discovery, unprecedented. Benchmark. Future interstellar comets will be compared to 3I Atlas. Does next one show nickel emission, or iron dominant like solar system comets, or something else entirely? We build understanding one object at a time. The CO2 dominance is second major finding. Challenges models, forces rethinking of cometary volatile ratios. If interstellar comets are systematically CO2 rich compared to solar system comets, that maps to formation temperature differences, or gas chemistry differences, or radiation processing differences, parameters we can extract by measuring enough objects. The extreme velocity is third major finding. 7 billion year travel time implied, oldest object we have ever observed close up. Think about that. When 3I Atlas formed, universe was 6.8 billion years old, roughly half current age. First galaxies were still forming. Reionization recently completed. Milky Way was smaller, less massive, chemical composition different, metallicity lower, star that spawned 3. I Atlas could have been second or third generation, formed from gas enriched by earlier supernovae, but still lower metallicity than Sun. Could have been low mass red dwarf, still burning today, could have been massive star, died billions of years ago, supernova, neutron star remnant, or black hole. We will never know which. The planetary system that ejected 3I Atlas formed and evolved while comet drifted. Planets migrated, collided. Atmospheres eroded or accreted. Some planets may be lost to stellar encounters. System destabilized. Remaining planets scattered. Or maybe system remains stable. Still exists today. Still orbits its star, somewhere in galaxy. Unknowable from here. 3. I Atlas carries no marker, no plaque, no encoded message. just ice and dust and chemistry. The composition is the message, decoded by spectroscopy, read by astronomers, interpreted by models, tells story of formation, tells story of journey, tells story of another world we will never visit. Solar conjunction period offers no Earth-based observations. Parker. Solar probe becomes sole observer. Whisper imaging from inside orbit of Mercury, watching perihelion from unique vantage point. If Parker captures CME impact, that data alone justifies mission time allocated to Comet. If Parker misses it, we have gap in coverage. Critical window lost. December emergence is key moment. First post-perihelion spectra. First assessment of survival. Fragmented or intact. Brightened or faded. Composition shifted or stable. Those questions get answered in December observations, then continuous monitoring through early 2026, watching activity decline as comet recedes, watching tail shrink, watching coma dissipate, eventually falls below detection threshold. Catalog entry preserved, data archived, papers published, object remembered, and somewhere in deep space archive, decades from now, astronomers will access 3I Atlas spectra. Compare to newly detected interstellar objects, compare to sample return mission results if those ever happen. Compare to exoplanet atmosphere spectra, looking for chemical signatures, looking for patterns, building theory of planetary system formation, building theory of cometary chemistry, building theory of galactic evolution. One comet, one brief visit, one set of observations, but implications stretch across astronomy, astrochemistry, planetary science, stellar evolution, galactic dynamics, everything connects. 3. I-Atlas is a data point, single measurement in vast parameter space, but crucial measurement, ground truth we did not have before. Late reveal sitting in our preliminary data, not yet published, waiting for confirmation. Post-perihelion observations might detect noble gases, neon, argon, krypton, xenon. These gases are inert. Donna TM react, Donna duo TM to form molecules, just atoms, very low condensation temperatures. If 3I Atlas contains noble gases trapped in amorphous ice, those gases release during perihelion heating. If spectroscopy detects them in December, that constrains formation conditions, tells us how cold the source region was, tells us how fast ice is formed. Fast cooling traps gases. Slow cooling lets them escape. Noble gas ratios directly measure protoplanetary disk temperature and cooling rate. Rosetta measured this at 67 P. Argon to nitrogen ratio, revealed formation below 35 Kelvin. If 3I Atlas shows similar measurement, we compare. See if interstellar comet formation matches solar system formation, or differs, cold, dark, ancient. 3. I Atlas emerges from behind the sun in 40 days carrying answers, 7 billion years in the making.